Welcome to Homework Lib.
Over here we have the following graph in which we are given the velocity with respect to time, and we're told that the initial position at a time equal to 3 seconds of a car is equal to 13 meters. So in this case, we want to know what would be the position given the graph at a time equal to 9 seconds. So over here. So what we are going to do is first of all identify that we have two different sections of the movement from 0 to 4 seconds in which the acceleration is going to be negative, and then another region from 4 all the way to 9 where acceleration is going to be positive. As you can see, in both of these sections, we're going to have very specific values. So let's find the acceleration for each of them, and with that, we can plug that value into our equations of motion. So for the first segment, the acceleration is going to be equal to change of velocity over change of time. As you can see, we don't need to employ the instantaneous change of velocity, meaning taking the derivative, because since we know that we have a linear graph, the result is going to be quite straightforward. So the final velocity over here is going to be minus 5 minus my initial velocity, which is 20, divided by the interval of time, which is 4 minus 0. This is going to be equal to minus 25 4 meters per second squared. We can leave it like that on this section. We really don't need to go any further. And for the second section, what we're going to get is that the change of velocity with respect to time, just for clarifying in case it wasn't clear on the previous one, is final velocity minus initial divided by final time minus initial. Over here, we're going to take the final velocity over here, which is 5 meters per second, minus 5 meters per second, and we're going to divide it by 10 minus 4, which is 6 seconds. We end up with 10/6, which we can simplify as 5/3 meters per second squared for the value of acceleration. Now, the other thing that we need to know is what is going to be my initial velocity at this specific time. So for the first section of the movement, over here, from 0 to 4, I'm going to write down the equation of motion. From 0 to 4 seconds, the equation of motion is given by x as a function of time is equal to initial position plus initial velocity times time plus 1/2 of acceleration times squared. In this case, what we are interested in actually is the value from 3 to 4 seconds. The value for acceleration is given by the problem that we found the graph, so minus 25 over 4. And in this case, the value for time that is going to elapse from 0 to 4 is going to be equal to 1 second. Let me clean up these equations over here just to make it more clear. Times minus 25 over 4 meters per second squared times 1 second squared. This is going to be the delta x from 3 to 4. Over here, we're going to have 1 second as well. And the value for the velocity is unknown. So to get it, let's look at the function of velocity as a function of time. So this is going to be equal to v0 plus acceleration times time. The value for my initial velocity, in order to get the velocity at 3 seconds, is going to be 20 meters per second plus minus 25/4 of meter per second squared times the time that elapsed, 3 seconds. This gives us an initial velocity at this moment of 1.25 meters per second. So now we can plug in the change of position as a function of time to get the result for the first part of the movement. The change of position is going to be 13 meters plus the velocity that we just found times 1 second, which is going to give us 1.25 meters, plus 1/2 of minus 25 over 4 meters per second squared times 1 second squared. We're going to get meters as well. The change of x from 3 to 4 will be equal to 11.125 meters. So this is the position at 4 seconds. Now for the second part of the movement that we're interested in is the section from 4 to 9 seconds. We know that the initial position is 11.125 meters. We know that the initial velocity from the graph is going to be equal to minus 5 meters per second squared. And we know that the acceleration coming from the graph is going to be equal to 5/3 of meter per second squared. Sorry, the velocity without the square, of course. So now, remember that all of these values are at time equal 4 seconds. So the amount of time that is going to elapse over here is going to be 9 seconds. So delta t equal 9 seconds minus 4 seconds equal to 5 seconds. Thus, our equation of motion for x at 9 seconds would be x0 plus v0 times delta t plus 1/2 of acceleration delta t squared. Plugging in the values for getting our result, 11.125 plus minus 5 meters per second times 5 plus, I'm going to put it down here just to get a little bit more space, plus 1/2 of 5/3, now as a positive, meter per second squared times delta t, which is 5 seconds squared. Over here, of course, is also 5 seconds. So the final value for the position at 9 seconds would be equal to 6.958 meters, or approximately 6.96 meters. So this would be our final position after 9. We arrive to the time equal to 9 seconds. So that would be all. Thank you very much and have a good one.